So, this was the protocol that we had last time, right? So, let me wait for one more minute. Okay, and we also claimed last time that if phi is not satisfiable, then V always accepts. Okay, and the second claim was that, which we will show today, is if phi is satisfiable, then the probability that V accepts is quite small. So, it is smaller than Nm by q. Okay. So, so some of you had this question last time that why is this final check necessary? Okay. I mean, in other words, as I said that what is the strategy of the prover? Okay. So, suppose phi is not satisfiable, what is the strategy of the prover? Which polynomial will he send at let us say the first step? So, at the first step basically okay, let me just okay, so I will just erase claim 1 for the time, claim 2 for the time being. The strategy of the prover is that, I mean, if phi is not satisfiable, is at the first step, so he will send the polynomial sigma x2 to xn of p phi, okay, and this is a polynomial in x1. And since this one sums up to 0, okay, so this one together with the sigma operator on x1 sums to 0, it will the verifier will accept in the first round, and then he will pick some random point in the field and plug that in for x1 and ask the prover to verify again in the second round that it sums up to V1. Okay. So, the prover will again be able to do it. So, the strategy of the prover in the case when phi is satisfiable, his best strategy is to always basically send this polynomial with the required number of operators. Okay. So, in this case, this step is kind of redundant. Okay. I mean, basically by the definition, I mean by the definition of what the prover is sending, okay, it will happen that finally this will be equal to Vn. Okay. But the point is that, I mean, nobody has restricted the prover to send exactly this polynomial at every step. Okay. In other words, if you look at the other side, so suppose if phi is satisfiable, okay, so then also the prover wants to convince the verifier that phi is unsatisfiable. Okay. So, that is what he wants. In other words, he wants to show that the summation sigma x1 through xn p phi is equal to 0. Okay. But now if he just ends up sending this polynomial at each step, I mean the verifier will reject in the first round itself, because what do we have in the first round, that sigma yeah, so this will be greater than 0 basically. So, the verifier will reject and it will not even go to the second round. So, the prover will try to cheat, I mean he will try to send some polynomial, let us say p1 prime, which will make the verifier which will fool the verifier, and it will take the thing to the next iteration. So, that is what we have to compute, that what is the probability with which the prover will succeed in fooling the verifier for all the n iterations. So, yeah. So, if phi is satisfiable, then we claim that the probability that the verifier ends up accepting is at most nm by q. Okay. So, anything else? So, again let me emphasize this, I mean it will not harm us. So, the aim of the prover is to show that sigma x1 through sigma xn of this polynomial p phi is equal to 0. But what we have in the case when phi is satisfiable, what we actually have is that this sum is strictly greater than 0. Okay. So, somewhere we expect the prover to falter. Okay. So, let us look at the proof. So, the proof will be an inductive argument, and we will perform our induction on basically this n. So, the number of summations that we have. So, the number of summations. Okay. And before going into the proof, let me just make a quick remark, which is in fact the crux of this proof is the very in fact that is the only mathematical tool that we require is so suppose if we have a polynomial so if P is a polynomial such that degree of P is less than let us say some quantity d, then P has at most d roots. Okay. So, this is something which is known to us. I mean the proof is I mean the mathematical proof is not so obvious, but with little effort it can be shown. And so note that we are not working in the field of reals. Okay. Here we are working in the field of FQ, but even in FQ this property holds true. And a corollary of this fact is that if P and Q are two polynomials of degree at most d, then they agree on at most d points. Okay. Because if we take two polynomials P and Q, and if we consider their difference, so if P and Q are two degree d polynomials, the difference is also a degree d polynomial, and that polynomial again by our remark has d roots, and those are exactly the d points on which these polynomials will be equal. So, P and Q are two non-identical degree d polynomials, because if we take two identical polynomials, then they agree basically on all points. So, it does not make sense. So, I can just they are non-identical. Okay, so let us come back to the proof of the claim. So, we induct on n. So, suppose if n is equal to 1. Okay, so what we have is we have that sigma x1 So, this is greater than 0. So, now the prover sends the polynomial p1 hat. Okay. No, so let us write it this way. So, suppose P sends a polynomial p1 prime. Okay. And so, now there can be two cases. So, if p1 prime is indeed equal to p1 hat, then what happens? So, the summation is greater than 0. Okay. So, then the verifier will immediately reject. So, if this is the case, then p1 prime 0 plus p1 prime 1 is greater than 0 by this observation, and therefore, we will reject. But now suppose the prover decides to cheat the verifier and he sends some other polynomial. Okay. So, suppose the polynomial that he sends is not equal to p1 hat. So, what happens in this case? Huh?
Maybe that is that it is 0.
Yes, if he sends a different polynomial, then it may be the case that p1 hat 0 plus p1 hat 1 is equal to 0. Okay. So, we do not know, I mean there can be many polynomials which satisfy that equality. But then what happens? So, now the verifier, he picks a random point Ri in the field, I mean in this case it is R1, he evaluates p1 prime at R1 and he goes on to check whether p1 hat of R1 is equal to V1 or not. Okay. Or so, in other words, so now for a random point picked by the verifier in this field, what is the probability that these two polynomials are identical on that point? Okay. Yeah. So, this is less than or equal to m by q, because there are both the polynomials have degree at most m. So, there are at most m points on which they agree upon, and the total number of possible choices is q. Okay. So, even if the polynomials are not equal, the probability by which the verifier will be fooled is at most m by q. Okay. So, in this step the verifier ends up accepting with probability at most m by q. So, is this clear to everybody? So, suppose what we are claiming is true for n minus 1 summations. Okay. So, now let us look at a case when what we have is sigma x1, sigma x2, sigma xn. So, we have n summations and the prover wants to and what we have is p phi of x1 through xn is greater than 0. So, what happens in the first round? So, again in the first round, if the polynomial sent by the prover, let us say p1 prime, so if that is equal to p1 hat, okay, so then we immediately rejects, again by the same thing, because we are summing up x1 and I mean he will find that that summation does not equal 0. Else So, these polynomials are not the same. So, V picks R1 in FQ, and again the probability that P1 hat R1 is equal to P1 prime R1 is at most m by q. And so, suppose if this happens, suppose if V ends up picking an R1 for which these two polynomials are the same, we will just say that if that happens, then P succeeds. Okay. So, he succeeds in fooling the verifier. On the other hand, suppose he picks if the verifier picks an R1 for which these two polynomials are not the same. So, else, so this was one case, V picks R1 such that P1 hat R1 is equal to P1 prime R1. So, that probability occurs, so the probability of that occurring is m by q. Else, the V1 that the verifier computes, which is nothing but P1 prime at R1. So, this is not the same as P1 hat R1, which by definition is equal to what? Is equal to x2 up to xn p5. The first point it is evaluated at R1 and the remaining are the bound variables. Sorry, this will be from x2. Okay. So, let us again go through this. So, let us look at case by case. If the polynomial that the prover picks is equal to P1 hat, then the verifier immediately rejects. If he picks a polynomial that is not equal, but the verifier picks a point on which the polynomials agree, then we will just claim that if that happens, then the prover succeeds and the probability of that happening is so much. And the third case is that if the verifier picks a point on which the two polynomials do not agree, then we have a V1 that is not equal to this summation. Okay. So, now we can use our induction hypothesis that now we have an n minus 1 summation. So, by our induction hypothesis, probability with which the prover succeeds in convincing V that this false claim is true, that is V1 is equal to sigma x2 up to xn p5 of R1 x2 to xn is how much? Is less than or equal to n minus 1 m by q, right. because that is what our induction hypothesis is. So, we want to show that so I had erased claim 2, but the probability with which V accepts is Nm by Q. So, our hypothesis is this is at most n minus 1 m by q, but so now what is the total probability that V accepts. So, the probability that V accepts is either he picks a point on which the polynomials agree, which is m by q, or he picks a point on which they do not agree, in which in the successive rounds somewhere the prover will be able to I mean somewhere where the verifier will be able to detect this error with probability at most or at least 1 minus that. So, the probability that V accepts is n minus 1 m by q. So, this is n m by q as we want. Yeah, which part? Oh, because these are the two things that can happen, right. So, either the V picks a point on which these two polynomials agree upon. If they agree upon that point, so then we say that the prover actually succeeds. So, it will go on to the next level anyway, and the probability of this happening is at most m by q. On the other hand, if he picks a point on which they do not agree, then the prover is left with an incorrect claim to prove in the successive iterations. Okay. So, then the prover has to prove the following thing, that V1 which is actually not equal to this. So, he has to prove this incorrect claim, okay. And that by our inductive by our induction hypothesis is at most n minus 1 m times q. So, it is so nothing I mean very deep happening here, it is simple induction. So, what is our induction hypothesis? So, our induction hypothesis, so let me start from there. So, our induction hypothesis is that suppose the prover wants to prove an incorrect claim. Okay. So, here we have n summations and we want to, and what we have is that this summation is greater than 0, and the goal of the prover is to show that this is actually equal to 0, and we assume that if I mean the prover succeeds with probability at most n m by q. So, that is our induction hypothesis. So, if we have n such summations, the prover succeeds in showing that p phi x1 through xn is equal to 0 with probability at most n m by q, if we have n summations. So, in other words, if we just instead of keeping n as our induction variable, you can think of that as k also. So, now what is happening here? So, suppose so if these two polynomials are the same, then it is easy. If these two polynomials are not the same, then we know that these two polynomials can agree on at most m points. So, if the verifier picks a point on which they agree, so that can happen with probability m by q, and here we claim that the prover has succeeded at least in this iteration. So, the thing moves on to the next iteration. Okay. So, again in that iteration the prover will send some polynomial p2, some polynomial p2 prime, the verifier will pick a random point r2, and the prover has to convince the verifier that those two things are the same. Okay. So, again that can happen with m by q or the next round. But the other case is that if the verifier picks an R1 on which these two polynomials do not agree, then what we have is that again what we claimed in our induction hypothesis, that he is left with an incorrect claim to prove in the remaining n minus 1 iterations. That is, he has to now show that V1 is equal to this quantity, but actually that is not the case. I mean actually from the way V1 is defined and the way P1 hat is defined, these two quantities are not the same.
If it is not equal,
but the verifier cannot check that, right. I mean the only thing the verifier checks is whether P1 prime 0 plus P1 prime 1 is equal to V0, okay. And then he picks an R1, he computes V1 and he sends V1 to the prover. Now the prover has to come up with a P2 prime, okay, such that P2 prime 0 plus P2 prime 1 is equal to V1 and so on. But now the prover himself knows that no matter what he does, that is not the case. So his best bet is to somehow cheat the verifier, okay. And by our induction hypothesis, he can do that with probability at most n minus 1 m by q. So these two events are exclusive events. So the probability of them happening is at most this plus this. Okay. Yeah. So as I said, I mean the only mathematical tool or the only deep mathematical observation that is being used in this theorem is that a polynomial with d degree cannot have more than d roots. So that is what they use. So now it is very easy to extend this argument to sharp p. So what we have shown is sat bar is in IP, but we can easily extend this and show the following. So let me define a language before stating the theorem. So let sharp sat D, so D stands for decision, is the following decision problem. So we are given a 3CNF Boolean formula phi and some number k in binary such that phi has exactly k satisfying assignments. Okay. So this is just the decision version of the sharp sat function. So what we can show is that this language is in IP again, and the proof is exactly the same, but with just some trivial modifications. So recall how did we construct this polynomial p phi in the case of sat bar. Okay. So the polynomial that we constructed was we replaced every positive literal with variable xi and a negated literal with 1 minus xi. If we had an OR, if we had OR of two literals, we just took their sum and for AND we took the product. So here what we do is, so suppose if we have a clause which is an OR of three literals L1, L2, L3. So we replace it with the polynomial 1 minus L1 hat, 1 minus L2 hat, 1 minus L3 hat. Okay. And what this gives us is that if this is satisfiable, then this evaluates to 1, and if this is not satisfiable, then this will evaluate to 0 from the definition. Yeah, so what do we have? So there are some small changes now. So the first change is that the polynomial corresponding to a clause now has degree 3. Okay, so earlier it had only degree 1. So the total degree of p phi was just m, but now degree of p phi can be as large as 3m, right. But this summation x1 through xn, how large can the value of this summation be now? So, earlier we had claimed that it would be as large as 2 to the power n times 3 to the power m. Yeah, so that will be exactly the number of satisfying assignments, and more specifically that will be bounded by 2 to the power n, or more generally. Yeah, so now basically we can choose our prime to be some number that is greater than 2 to the power n. So now what we have to show is that this summation sigma x1 through xn of p phi is equal to k. So this is what we have to show, and the thing proceeds exactly in the same manner. Okay. So now let us look at our main objective. So the main objective with which we started this entire program was to show that the class P space is contained in IP. Okay. So what we have shown so far is that a class which is as large as sharp P is contained in IP because of this observation, but P space is even bigger than sharp P. So how do we show this? So again you can argue that, so let us look at P space complete problem. So we can look at TQBF. So yeah, so this language TQBF is basically a quantified Boolean formula. Let us call it psi, where every variable is quantified. So let us say that the variable x1 is quantified with there exists quantifier x2 with a for all, and finally xn is quantified with a for all quantifier, and we have some unquantified 3CNF formula at the end. Okay. So I am just assuming n to be even, does not matter. So this problem is complete for P space. So this we had at least claimed at one of our earlier lectures. So how do we show that there is some IP protocol for this problem? So TQBF stands for true quantified Boolean formulas. Okay. So it is set of all Boolean formulas phi such that for some assignment to the variable x1 and for all possible assignments to x2 and so on up till xn, this will evaluate to true. Okay. So it is basically the same as SAT, but in SAT every variable is unquantified. Okay. So basically for some assignment to x1 and some assignment to x2 and so on, the formula should evaluate to true. But here certain variables are also quantified with a for all quantifier, that is, no matter whether you choose 0 or 1, it should evaluate to true. So what is the I mean what would the strategy be in this case? So here again we can construct our polynomial as follows. I mean what we can do is we can construct, so from phi we construct, let us say, our polynomial P phi, and now for the for all quantifiers I consider the product with, I mean over x1 coming from 0 1, and for there exist quantifiers I can again look at it as x1 being summed over 0 1, and then our goal is to show that this is basically not equal to 0, because we want all true formulas. Okay. So, this is the algebraic version of the problem. So, earlier what we had in the case of sat bar, what we had was that all the variables were getting quantified with a summation operator, okay. But here, because of the for all, certain variables are getting quantified with the product operator. Okay. So, till this point there is no problem, I mean we can do this, but now there comes a problem. So, what happens if we do this? So, where will the degree blow up? So, how exactly? So, what was the protocol for let us say sat bar? Okay. So, basically the prover sent a polynomial P1, okay, let us say P1 prime, and the verifier needed to check whether P1 prime 0 plus P1 prime 1 was equal to some quantity. So, in that case 0, and then send back a random point on which again it had to convince. So, in this case what the verifier can do is it can basically compute the product, I mean it can compute P1 prime 0 times P1 prime 1. Okay. So, that can be done, but yeah, so as you said the degree will blow up, but the degree blows up, but the degree of which polynomial? So, what blows up in this case?
The one which we are evaluating is the P1.
Yeah, so precisely. So, basically the polynomial that the verifier, I mean the polynomial that the prover is sending. So, that, because see what is happening here. So, here when we are summing up over a variable, then we have no problem, but when we are taking the product over this variable, we are basically doing something like this. So, suppose if we do a product of sum xi of a polynomial p on x1 up to x1 through xn. So, what does this mean? So, this is equal to p of x1 through xi minus 1, 1 xi plus 1 to xn times p of x1 through xi minus 1, 0 xi plus 1 through xn. Okay. So, if p had let us say degree d, the product polynomial will now have degree can have degree at most 2d. Okay. So, in other words, if we take this product too many times, if we take this product for example order n times, the thing can go up to 2 to the power n. Okay. So, the polynomial that the prover needs to send, on which the verifier will get convinced, can have degree as large as 2 to the power n. Okay. So, this is why, and now since the verifier is just a machine which has a polynomial time restriction, it cannot evaluate anything that is that large. So, what is the idea? So, the idea again is very simple. So, as I said that all these work kind of happened in a very short span of time, and this result showing that p space is contained in IP was done by Shamir. So, what he observed is that suppose if we have a variable x, okay, which belongs to 0 1, then x is always equal to x to the power k for any k. So, he made this simple observation that if x is 0, then x to the power k is equal to 0, and if x is 1, then x to the power k is again equal to 1. Okay. So, of course, this does not happen for other values, but it is sufficient for us, because we are only dealing with inputs from 0 and 1. Okay. So, then what he said that, okay, so with this observation what we can do is, although the polynomial's degree keeps on growing at each stage, we can, using this observation, we can reduce it, and that will not have any effect on the value of the polynomial. So, in other words, so suppose if we have a polynomial p phi, okay, over x 1 through x n, then the value of this polynomial will be equal to, let me call it L x I of p phi, which is defined as x I p phi of x 1 up to x I minus 1, 1, x I plus 1 up to x n plus 1 minus x I up to x n. Okay. So, suppose if we have some polynomial on which the variable x I has degree that is greater than 1. Okay. So, suppose it has degree 2. So, let us take a small example. So, suppose we take a polynomial x 1 square x 2 plus x 2 plus, let us say x 1 to the power 4 x 2, okay, and we apply this operator on this polynomial. So, what would L x 1 of p be? So, first we substitute 1 for x 1. So, if we substitute 1 for x 1, we have x 2 plus x 2. Okay. So, we have 3 x 2, and now if we substitute 0 and multiply it with 1 minus x 1, we have 1 minus x 1 times x 2, which is equal to 2 x 1 no, this was actually 3 x 1 x 2. No. So, it is x 1 times this polynomial. So, it was 3 x 1 x 2. So, we have 2 x 1 x 2 plus x 2. In other words, what we are doing is that we are reducing the degree of x 1 to 1, and then we are just collecting the terms. Okay. So, this operator has that property. So, yeah, so what Shamini did was, so he said that together with there exist together with the sum and the product operator, if I intersperse them with operators with of this kind, which will reduce the degree at each step also, and then come up with an appropriate protocol. So, that will be able to take care of the class P space or this language TQBF as well. So, that was. So, we will talk a little bit more about this next time. So, let us stop here.